So we can see now our basic job is to calculate the changes in energy. So let's embark on that in earnest. So I want to calculate En minus E sub n minus 1, which is my definition of the change in energy. Now, we're going to do that with our spectrum that we've calculated for hydrogen, which is this somewhat complicated formula. And we want to find some principle to organize our algebra. Now, you'll notice if I subtract this from the same formula with n minus 1, I'm going to have to keep writing down these prefactors where really the main focus should be on what's going on with n. So a neat trick we can do to simplify our writing is to divide by the energy E, or if you want to be very specific, the starting energy E sub n. Because when I do that, you'll notice that these prefactors will cancel out in the division, and I can focus on what's going on with n squared. So delta E is, of course, those constants times 1 over n squared. So the change in delta E will just be the change in 1 over n squared with those constants, which I could then pull out. And then the energy itself is, of course, those constants times is equal to those constants times 1 over n squared. And then those constants would cancel with the constants in the numerator. So this expression you should be able to see is exactly equal to the one on the right. The beauty is once I have this evaluated, it will be quite easy to recover the change in energy. I would then just multiply my result by energy. Now let's proceed to evaluate this. So that's actually just n squared times the change in 1 over n squared. And there are two ways actually to evaluate this change. The first way is much more efficient, and that is to realize that, well, again, as n gets very large, it has some value like 1,000,000. And the difference between 1 over 1,000,000 squared and 1 over 1,000,001 squared is very small. That means that this function is behaving very continuously as a function of n for large n. So I should be able to approximate it very well with a simple Taylor series expansion. So that I could write this as n squared times the rate of change of 1 over n squared as I change n, times then the actual change in n. But if I am looking at changing n by simply the value 1, delta n becomes 1, and I don't have to worry about that term. And now I merely have to take the derivative of 1 over n squared, which is simple enough. That's just minus 2 is the exponent, and I get 1 less power of n, so that's n cubed now in the denominator. So the final result of this analysis is minus 2 divided by n. Now, just as a quick aside, if you wanted to verify this, we can do the algebra directly. And I'll do it just this once because this is the first time you're kind of seeing this sort of thing. So if I did n squared times the change in 1 over n squared, that would be equal to n squared times 1 over n squared minus 1 over n minus 1 squared. And I won't lead you through all of the algebra, but if you do it quickly in your head, you will realize, well, I'm going to put these onto a common denominator, but then the n squared here in the numerator will cancel one of the n squared, cancel the n squared in the common denominator, and I'll be left with n minus 1 squared in my denominator. In my numerator, I then get the difference between these two terms, and when I square them out, the n squares will cancel, and I'll be left simply with minus 2n plus 1. And I think you can see very easily that if n becomes very large in that limit, these constants here are negligible. Those become negligible. And then I'm just left with exactly, to a very good approximation, minus 2 over n, which is exactly what we had concluded with the derivative argument. Now, either way you want to carry out that analysis, our result is quite clear, and that is that the change in energy in our state is going to equal the product of the energy times my factor here on the right, so it'll give me minus 2e divided by the quantum number n. That's my result. Now, there were two things we wanted to verify about this. The first thing is that if we go into the classical limit and take this limit where h bar is going to 0, do we in fact find a continuum of energies so that the spacing between these energy levels vanishes so that we would never notice it and it can vary continuously as in the classical spiral case? Now, in this limit, as h vanishes, n is headed towards infinity, and you will notice in our expression we are dividing our energy by this very large value of n, which is getting larger and larger. So yes, indeed, the energy change will approach 0 as h bar vanishes, which of course also means n goes to infinity. So that is nice. We have then a continuum, as in the classical case. The more subtle question is whether or not we get the correct frequencies out. So the question is, does this delta E, this energy change, actually give me what we were saying here? Does it really give me Planck's constant divided by the classical period? T over H over T classical. So this is a question mark, something we have to prove, which of course is the same as saying, as we had derived up above, h bar over m times the momentum over the radius. Well, the best way to evaluate this is let's look at this right-hand side and see what it gives us. So we have Planck's constant divided by the electron mass. We now have to substitute in the ratio between the momentum and the radius. Those quantities, fortunately, we do understand in terms of energy. The momentum is the square root of minus 2me, and the radius actually is the Coulomb pieces divided by minus 2e. So I think I can remember that. I had in the numerator the square root of minus twice the mass times the energy. And in the denominator, I had the Coulomb pieces, Coulomb's constant e squared, divided by minus 2e. I think I got that second part right. Maybe we better check it. Where is it? Right here. Exactly. Perfect. Now, this looks very promising because immediately we can see that this minus 2e will come up into my numerator, and that is looking a lot like my quantum mechanical result. It has a factor like that. So I'm going to, first thing that I want to do is to move this minus 2e factor into the on top part, minus 2e. And then having taken care of this factor, I have the remaining pieces, and it looks like they really want to be combined together under the square root sign so that I can then compare them with e. So let me do that. Let's bring these into the square root sign. And I notice here now this factor of minus 2e is appearing once again. Since that seems to occur so often, I'm going to keep those two together. So I'll have a minus 2e. And then these other terms, I've taken care of those. These other terms are going to, inside the square root, either be in the numerator or denominator. So let's make a nice fraction. H bar will come on into the square root, where it will become h bar squared. So let me do that. The mass m is in the numerator, but that when I bring in the outside mass, that will put 2 in the denominator, so I get a net mass into the denominator. And the final factors that I have is Coulomb's constant e squared. These Coulomb pieces, if I bring them inside the square root, I get them there, except now they will become squared. So I will copy that down. And now I've taken care of, I hope you can see, all of my factors. The big question now is, what does this piece give me? Does it actually evaluate to the 1 over n that I need for the classical and quantum physics to line up perfectly? Now, to answer that, of course, what we need to do is to insert our result for the energy. Now, for the energy from the quantum mechanical case, we have this expression. It has a minus 1/2 mass times Coulomb pieces squared over h bar squared n squared. So I guess we'll copy it down here so we can do a little bit of the work. So the energy then down here, if we remember, has a minus 1/2. It has the mass times the Coulomb pieces in the numerator squared divided by h bar squared. Now I want you to notice some things. When I insert this in for E, the minus 2 will cancel the minus 1/2. The mass in the denominator is going to cancel the mass in the numerator. The Coulomb pieces squared in the denominator are going to cancel the Coulomb pieces squared in the numerator. Planck's constant squared in the numerator cancels Planck's constant squared in the denominator. It looks like everything has canceled out except I made a small mistake. The energy had those factors, but of course it also has the 1 over n squared. So the energy I substituted should have had a 1 over n squared. So you'll notice I checked off all the pieces in here. All of these terms out here cancel all of these terms here. All that is left out of the inside the square root is just 1 divided by n squared. And of course the square root of that just gives me, look at that, 1 over n times minus 2e. And that is exactly what we needed for the radiation coming out to match what we would expect from the classical case. So this gives us complete correspondence between the classical and quantum theory and the limit that Planck's constant disappears. And this is really what Bohr meant by the correspondence principle. We had previously expressed it as a more general principle about recovering classical physics, but I think it's worthwhile to note that the first context in which it was really considered was this context of the matching up of the spacings between energy levels.